Welcome to this video with an example of analyzing determinate structures. This is one of several videos in a short course on equilibrium posted at terje's Toolbox, a website that contains notes, examples, and algorithms for structural analysis. The example covered in this video is intended to reinforce the following formulas for the bending moment diagram and shear force diagram for two basic beam cases. This slide was included in the video on determinate structures in this short course. One beam case, shown at the top, is a cantilevered beam with either uniformly distributed load or a point load at the tip. It is easy to derive, and good to remember, that the bending moment at the base of the uniformly loaded cantilever is QL²/2. The shear force is the full load, namely Q times L. The bending moment value for a point load, denoted by P, is naturally P times L. The shear force is P, because that is the full vertical load on the beam. The beam case shown below is a simply supported beam. That means it has a pin support at one end and a roller support at the other end. This is an extraordinarily important structure, because analyzing it reveals how the bending moment varies between any 2 points of any beam case. When there is uniformly distributed load on the simply supported beam, then the bending moment value in the middle is QL²/8. We derived this result in an earlier video in this short course on equilibrium. In fact, we have already seen that the parabola for the cantilevered beam above is also a QL²/2 parabola. Again, the simply supported beam case is important because analyzing it reveals how the bending moment varies between any 2 points of any beam case. Next, the shear force at each end is half the total load, namely QL/2. When a point load, P, acts at the middle of the beam, then the bending moment at that location is P times L/4. This is easy to derive if we first calculate the reaction force at the supports, and then calculate the bending moment at the middle. Those reaction forces are, in this case, half of the load, P, at each support. The structure we consider in this video has a fixed support on the left-hand side, a roller support at the right-hand side, and a hinge that releases the bending moment near the middle. In the short course on indeterminate structures, we learn how to find the degree of static indeterminacy. It turns out that this structure is statically determinate, which means we can find the internal forces by equilibrium alone. The standard procedure for analyzing determinate structures is to start by calculating the reaction forces. However, it is often possible to identify the basic beam cases in order to do things quicker. That is the purpose of this video, and for this structure, we notice a simply supported beam between points B and C. In other words, we see the moment is 0 at point B because of the hinge at that location, and we see that the moment at C is 0 because of the roller support there. As a result, the beam in between is a simply supported beam. That means we immediately have the bending moment diagram and shear force diagram below, from the basic beam cases. Next, we look at the beam between A and B. It has no distributed load, but it is holding up the simply supported beam that we addressed a moment ago. That means the beam from A to B is a cantilevered beam with a point load at the tip. That point load is equal to the force needed to keep the simply supported beam supported at point B. In other words, the shear force from the simply supported beam is the point load acting on the cantilever at point B. As a result, we have the bending moment diagram and shear force diagram below, from one of the basic beam cases. The diagrams on the next page summarize the solution we found, solely by using basic beam cases. Thanks for watching this video. Please visit terje's Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.